So we're looking at 8.4 here. I think this is a pretty challenging section. I believe, if I remember right, 8.5 as well. If I were teaching a course on this, I would not include this. It's not something we would normally get to in a college algebra course. So if you're taking a course with me, this would definitely be optional. However, I'm going to show you what this is. I got a calculus book out to try to refresh me on trying to see why the formulas in this work, and I believe this would drop into a calculus 3 topic. So it's a little intense that they're putting this in college algebra. I think the 8.1 through 8.3 are fair game, but this is a little bit much. But I'm going to take you through it if you're interested or whatever you're going to use it for. So in our first three sections, this part's fine. This would be fair game, but we've been looking at conic sections. We've been looking at ellipse, hyperbola, parabola, and we haven't really talked much about a circle. But a circle is just the same formula as an ellipse, where the a and c terms, the terms in front of x squared and y squared, are the same. It makes it a circle. So the first question we're going to ask here is, how could we, looking at these standard forms, or I'm sorry, these are the general forms of each of these conic sections, could we identify them? Now, we'll look at this quickly here. Do you remember, if we had, these are not in the standard form. So the standard form of an ellipse, something like this. Okay, it doesn't really matter what the numbers are. The point was that it was a positive between the two squared terms. And so if you look here, if we were to divide through here, so to create this in the standard form, we have the two positive terms for the x and the y, right? So if I were to divide through here by some number to get this into the standard form, this would be an ellipse. Now a circle is exactly the same thing, except its a and c term are going to be identical. So a circle turns out to be something like x squared over 9 plus y squared over 9. They're over the same number there in order to make the axis. It's identical in each direction. So it's an ellipse where the major and minor axis are the same length, which makes a circle. Okay, now a hyperbola was the same equation as this. Now, of course, there's different versions. I'm just going to show you one. Do you remember? So you had a negative sign in there. Okay, so that would make an ellipse. Well, if you look here, if you divided through by something in order to get this in a standard form, some number, this is going to create one positive and one negative. It's going to make that formula for a hyperbola. And then lastly, we had different versions of this as well, but we saw parabolas where we were doing something like this. So they aren't going to have two squared terms, they're only going to have one. Either an x squared or y squared, but not both. That's how we could identify the parabola. Now, before we move on, this is going to be the easier part of the section. The harder part is going to ask us to do something called the rotation of an axis. Now, notice in this formulas, in all of these formulas, that there is no xy term. So look here. In all of these that we've studied so far, there's no xy term. If we had this term, we're going to run into trouble, and we'll talk about that in a bit. I just wanted to point that out to you, that we're going to come back to this idea of this xy term. None of ours so far have this xy term. Okay, so let's start identifying here for our formulas. So if we look through here, I notice that the x squared and the y squared terms, I've got one with a negative sign. And so this is going to make me the hyperbola. So if we go back here, this was my hyperbola, where I had a negative in between them. So if I have this negative, I have a positive and a negative in the x squared and y squared terms. Doesn't matter the order there, but I want one of each. This is going to make the hyperbola. Notice here in B, I only have a y squared. I don't have both. So this is going to be a parabola. Now I have positive x squared and y squared terms. So I would be thinking ellipse, but because the coefficients in front of them are identical, this makes a circle. Okay, now this one they're trying to trick us here. So we have two negative coefficients in front of x squared and y squared, but if I were to divide through by a negative number, this is going to create both x squared and y squared to be the same sign. They're both going to be positive. So this is a little deceptive, but these are going to wind up having the same sign when I put this in standard form. So this is going to be an ellipse. Okay, now try a couple of these on your own if you want to pause the video. I'm I'll talk you through it now though. So if I'm looking here, I've got opposite signs on the x squared and the y squared terms. This is going to be a hyperbola. And if I'm looking here, I've got both positives on the x squared and y squared terms. This is going to be an ellipse. It'd be a circle if they had the same coefficients, but they're different. Okay, now that's the easy part, and I think that's fair game, but here's where things get a little crazy. If we have that xy term, so again, I mentioned to you that all of our formulas that we've looked through for the conic sections didn't have it. If you have the xy term, what it means is that your hyperbola, your ellipse, it's been rotated diagonally through some angle. And this is what I was trying to go back into the calculus book to see the definition of this. The OpenStax book, always grateful for it, but it didn't really have much of a proof of these, or at least I didn't see it. So I went to the calculus book, and this is pretty intense. Both of these are going to require some trig identities and some careful thought. I thought this was going to be a simple, obvious explanation, but it's not. So it has a proof. I don't have it memorized. It's in a calc book for you, but here's what we're saying. We're going to take that the value of x is going to be rotated through some new angle alpha here. So we have rotated the x and y axis. So normally we're like this, but what this is saying is we're going to take it, well, let's do it like this. And we have now rotated it through some new axis. And we are going to look at the equation in terms of this new rotated axis. Okay, so we'll come back to these formulas. Let me show you the next slide and show you where this is going. Okay, so we want to see how to represent x and y when we've rotated them through this new axis. And so what we're going to do, here's x in our normal scale, our normal axis. Here's y in our normal axis. We're going to use these formulas to show what they would be in this new rotated system. So this one's going to be pretty easy. What we're going to see is that we've rotated 45 degrees. So this will tell me how to convert them between our regular axis and our rotated axis. So we have this new x prime. So we have a new x prime and y prime that live in the new rotated axis. So we're going to just they're going to stay these primes. We won't be able to eliminate these. But we know the cosine of 45 is 1 over square root of 2, or it's really radical 2 over 2, but they're just leaving it here because it's going to make the computation a little easier. They're leaving it as 1 over radical 2, same thing. And we know the sine of 45 is 1 over the square root of 2. Okay, now hopefully you can follow the algebra. They're just getting a common denominator. And now our x in this new rotated system becomes all of this, where x prime and y prime are the new rotated x's and the new rotated y's. So let's do it again. Now we're going to rotate y. So in our system we call it y, but in this new rotated system we use our formula here where we're going to find sine of 45 plus cosine of 45. So same thing, and now we have in our regular Cartesian system, this is y. In our new system, this rotated system, y becomes x prime plus y prime all over radical 2. So we're converting from a regular orientation to use these two formulas to put it into this new rotated system where x prime and y prime are the new x and y off that rotated axis. So it's the x and the y off these. So here's my x, here's my y. But they're primes now. X prime and y prime are those new rotated axes. Okay, so we have found, so our formulas here have found x and y to convert. This is our dictionary, converting it between the regular system and the rotated system, each of these. Now, let's go back to our original equation. And what we're going to do is put these new versions of x wherever there was an old version of x. We're going to put the new version of y wherever there's an old version of y. And what's going to happen, because we've adjusted for the rotation here, is it's going to eliminate this problem section. It's going to get rid of the xy term. It's going to fall out. And then we'll have something that could be graphed on this new rotated axis. If we use the new rotated axis and graph just like we used to graph, we would get the correct picture. So let me show you. So we're substituting in here anywhere there was an x, we're replacing it with our new rotated x. There was an x here, new rotated x. This is our new rotated y, new rotated y. Now the math here is going to be very unpleasant, but we literally have to square these, got to distribute these. So I know this, like you saw me hit this one, it's going to be a little overwhelming, but we really are just doing some basic algebra here. I'm foiling out this binomial. Do you remember it always makes the middle term, 2 of the middle term. Just FOIL it, you'd get this here. What else? I'm foiling this out. And then that's a perfect square binomial, so it's going to make this. Now we're foiling this out again. So all of this is just standard stuff. I know there's primes. It looks crazy, but it follows all the normal algebra rules. So we were able to cancel. So yeah, here on the bottom, we have the square root of 2. So remember, you can give a square to both the top and the bottom. So I've squared the top, and I've squared the square root of 2. That's where this 2 came from. I've squared the square root of 2, and then they could cancel those down. Down here, the same thing. I gave the square to the top, I gave it to the bottom. That's how I got a 2 down here. The 2's will cancel. Okay, so this is where we've gone here. We're now combining like terms, and look what happens. That rotated term, the x, y prime, are gone. That rotation part has disappeared. And they're just tidying up now. So here's what would be left. They're getting rid of this 2 by just multiplying it all the way through by 2. Just like how you would clear out a fraction if you were doing kind of a basic algebra problem. This is just a trick to clear out the 2 on the bottom. Okay, so anyway, now we get all the way to here. There's really nothing special going on, just that we have stuff with primes in it. That's it. Okay, and then again, yeah, they combine like terms. This is all nothing. So I'm combining x prime squared terms. I know that's weird, but we can do it. Y prime squared terms. We're putting all this together. We get down to here. Now, we always want our, what is this one? Yeah, this is an ellipse. So we always want these to be equal to 1. So they've divided through by 60. We saw this trick in the earlier sections, and this is what we create. Now, it's an ellipse, but we can build it if we use our new oriented axis with the x prime and the y prime. We can build it off the diagonal here. So the square root of 20 is my length for my major axis. The square root of 12 is my length for my minor axis. But we're going to build it literally on our new axis. We're going to turn our head and pretend we're working off this new red axis. Okay, now I hope that made some sense. Now we're going to do this again, but we're going to start from scratch here. And so the steps are there, but let me show you. We don't have anything to start with. We don't know the angle. So we're going to need to find that angle, and we're going to set up a triangle just like we would in trigonometry in order to help us make those the rotations that we need. So let me talk you through this. I thought this was also going to be an intuitive formula here. I looked this back up in the calculus book. It's not. It requires some, we're going to use some half angle formulas, I think, and then some sum and different formulas, I think. But anyway, it's not intuitive, and I'm going to leave the proof to someone smarter than me in a textbook. But to find our angle, here's what we're going to do. We're working with a double angle for cotangent. So just trust me here. Again, check out a calculus book if you care where this comes from. I don't think I certainly am not ready to explain it to you right now. But this is our formula. We're going to take the coefficient in front of A. We're going to take the coefficient in front of C, which is the 17. And then this is our B term. Okay? Now, we're going to just follow this formula, tidy this up, and we get down to 3/4. So we have the cotangent of a double angle that's equal to 3/4. Okay, well, cotangent is adjacent over opposite. So let's find this missing hypotenuse. We always fill in the triangle. Whenever you got a triangle, finish it. So if you're familiar, you're good at trig, you know this one's standard. So it's 3 squared plus 4 squared equals h squared. But this is a 3, 4, 5 triangle. That's always what happens with a special angle there. So we've got 5. Okay, now we're going to use half angle identities to finish solving this. So we have a double angle. We want to know what just regular sine and regular cosine would be. So these are formulas off your normal trig formula sheet. We're just dropping stuff in here. So where am I getting this cosine of the double angle? I'm just getting it from my triangle. Cosine of this double angle would be 3 over 5. Sine would be 4 over 5. Okay? Now actually we just need the cosine, don't we, for this formula. So we're putting it in here. We're putting our 3 and 5 into both of these formulas. Now I'll let you, this is some basic fraction math here. Gets us down to all of this. So this is something I hope you could just follow them and it would make some sense. And here we get cosine comes down to all of this. Okay, we now have sine and cosine. Okay, well, why did we need those? Because we needed them for our rotation formulas to convert x and y between the regular Cartesian system and the rotated system. So we're just plugging in now. I know cosine of theta and sine of theta. We know these from our triangle that we've created. We never actually knew the actual angle, but we have the trig from the triangle we made. Okay, so we do this, simplify down, we get to here. Making those substitutions again, getting down to here. Hold on. Oh yeah, I was wondering where these come from. So again, these are ending with square root of 5 just because of the half angle formula there. Okay, that confused me. So here's our dictionary. In the Cartesian system, it's called x. In this rotated system, it's called all this. In the Cartesian system, it's y. In the rotated system, it's all of this. Now, we're going to go and do what we did in the last one. Wherever we had an x in our original formula, we're going to replace it with our new rotated x. Wherever we had a y in our original formula, we're going to replace it with a rotated y. Now, there is some heavy lifting here with all of the arithmetic, the algebra, I guess, but it's the same as we were doing before. I'm squaring the top and I'm squaring the bottom. That's where the 5 came from. We're going to FOIL this out. I'm multiplying the square root of 5 times the square root of 5. That's how I got another 5. FOILing this out. So squaring the top, squaring the bottom, that's where we got another 5. Okay, now all of these fractions have 5 on the bottom. I'm just going to multiply both sides by 5. And that's how, if I do it to one, I got to do it to the other. That's where the 100 came from. So this line has taken care of the fractions, has everything FOILed out. Now I'm sending the 8 through, the negative 12 through, the 17 through. And then here we are just canceling like terms. I know it's very strange, but these are like terms. Oh, I shouldn't do it like that. These are like terms. So if you put those together, you're going to see what we expected was the rotation term should now fall out. That's why we were doing this. We're going to match up all our x prime squared terms. We're going to match up all our y prime squared terms, and we get down to this equation. And you remember how we did this before. We didn't want this to equal 100. We want it to equal 1. So we divide everything by 100, and we get down to this. Now we have an ellipse on our new rotated system with a major axis of 2 and a minor axis of 1. Let's see if I got a picture. Yeah. So we'd be going, so we're using the new red axis. We're going 2 in each direction and 1 up and down. Connect it all, and there's our ellipse. Okay, now this is very difficult, but if you're watching this, then you care. So let's try to work through one of these together. So one more here. I'm even going to show you, this is what we're trying to get to. Our new rotated system, we should get this ellipse. Okay? Now, let's get started. We don't have the angle which we've rotated, so we're going to have to do this cotangent trick that we did, where we do the cotangent of 2 theta. Again, we're taking it for granted here where this came from. But we've got a minus c divided by b. Well, the a is 13, the c is 7, and the b is negative 6 square root of 3. So this is going to be 6 over negative 6 square root of 3. This is going to be negative 1 over the square root of 3. Okay, now we're going to build our triangle. And because it's cotangent, we have negative adjacent over hypotenuse, or a negative adjacent over opposite. So one of those has to be negative, and it's actually not going to matter. But I put this in quadrant 2. I made the adjacent the negative 1, and the opposite to be the square root of 3. So this is just some trig stuff here. I'm taking this trig identity and I'm putting it in a quadrant. Okay, now if we were to find that missing side, you ever build a triangle, you find the missing side. 1 squared plus the square root of 3 squared is going to be, that's going to be 4, and you square root it 2. I'm just doing the Pythagorean theorem to find that missing side. Now, what our formulas are going to need are the cosine of this new double angle that we've created. Well, the cosine here is going to be adjacent over the hypotenuse, so negative 1/2. Okay, now we're doing those formulas. I'm trying to write small because this is going to be, now we're going to do a half angle formula, which is exactly like we did before, 1 minus cosine 2 theta all over 2. And you're going to do the same for the cosine of the half angle, 1 plus cosine 2 theta all over 2. I didn't write that very well, but so you get a 2 on the top of the bottom. This is going to be like 2 over 2. So follow me here. These two minuses make a plus. 2 over 2 plus 1, we're going to get 3 halves over 2. I don't really want to show all this because there's so much coming, but can you agree, if you know your fraction rules here, this gets to be 3 over 4, radical 3 over 2. Okay, in a similar fashion, what are we going to get here? We're going to get, this is going to turn into 1/2 over 2. It's going to be the square root of 1/4, which is going to be 1 over the square root of 4, which is going to be 1/2. Okay, we now know sine and cosine, and so what we can do with those is we can put them into our new rotated definitions. So I don't want to rewrite it all. It's x prime cosine of theta. Well, cosine of theta is 1/2. And then it's minus y prime sine of theta. Sine of theta is radical 3 over 2. Okay, we're going to then rotate y in the same fashion. You're just using that formula. It's just, well, I wouldn't ask you to memorize it, but so sine is radical 3 over 2. And then we've got plus y prime times cosine of theta. Okay, now I have these. Can you follow that we can simplify this down to this? And we can simplify this down to this. Oops. Yeah, there we go. All right, now I would take this original formula, and everywhere there was an x, I'm replacing it with our new rotated version. And now this one, I'm right here, I'm replacing this y. Okay, square all that. Okay, I don't know if I want to write down for you what I have on this massive paper here. It's a lot to do, but it did work. It did work out. Yeah, I'm trying to think how much I want to show you. So remember that what we would do here. I would square this top, and the bottom is going to become a 4. I'm going to multiply, FOIL out the tops, the bottom's going to become a 4. I'm going to square the top, and the bottom's going to become a 4. So what winds up happening is everything is going to be over 4. So I'm going to multiply both sides by 4, and this is going to become 64. Yeah, I guess I'll show it if anyone is out there. I'm going to show you just what happens. That's an x. Oh, I did this right. This has got to have a square root of 3 there. That's actually the mistake I made when I first did it. So it was 6 square root of 3 there. Okay. Where was I? Okay. Believe it or not, if you FOIL all of this out, if you can even read my handwriting, this is what you get. This is supposed to be a 39 if you can't read that. 39. Okay. Now, if you combine like terms, I'm going to show you the terms and then I'm going to be done with this thing. So here are my like terms. And again, this is a 39. If you combine the like terms, the rotated pieces drop out, just like we would expect. And what we're going to be left with is 16x prime squared plus 64y prime squared equals 64. Now we want this ellipse has to be equal to 1 in standard form, so we're going to divide through by 64, and we get x prime squared over 4 plus y prime squared over 1 equals 1. And that's what we were trying to create. Again, I know this is really brutal, but if you are hardcore and you have actually given this a shot, well, there you go. We're rotating the axis. We got one more on this topic in our next video, and I can't remember what 8.5 is about, but we'll take a look at that too.